Hello, my name is Angelina Dominguez, and I teach AP Computer Science Principles at Veterans Tribute Career and Technical Academy in Las Vegas, Nevada. And I am excited to be talking to you today about binary numbers. It's an exciting day because we get to finally learn how binary works. So, what will we learn? I kind of just told you. We're going to learn about how binary works, right? We're going to convert binary to decimal, decimal to binary, and we're going to practice a whole bunch. So, let's get started. So before we talk about binary, we're, we're going to talk about number systems in general, because regardless of what number system you use, they all follow the same basic mechanics and rules. So first, let's check out these mechanics and rules behind the decimal number system. So let's look at this number 5012. We're going to break this number down and hopefully remember the mechanics behind the value of these digits. So I want you to just answer out loud to the next couple questions for me. What is the place value of the first place where the 2 is, all the way on the right? I didn't hear you. Good, the ones place. So we always start with the ones place. What's the next place value where the 1 is? The tens place. And the next place value? Hundreds place, and that last place value where the 5 is, the thousands place. Awesome. It's important to know why the value of each place is going up and by how much. So we're currently working with the decimal number system, or base 10. How many digits do we have? We have 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 10 numbers. Every time we move over a place, we multiply by 10 because we have exponentially increased the possible numbers we can have by 10. So we go the first place is 1 times 10, right? It gives us the tens place, 10 times 10 gives us the hundreds place, 100 times 10 gives us the thousands place, and so on. So this means we have 5 1000s. We don't have any 100s. We have 110 and we have 2 ones. We add those values together, and that's what gives us the value behind the digits 5012. So now let's try binary. How many digits does binary use? Correct, 2, a 0 and a 1. So I said a second ago that number systems follow the same basic mechanics and rules, so let's double check that statement. So here we have binary, or base 2, the number 1101. The first place value is always 1. When we were working with the decimal number system, we multiplied by 10 every time we moved over a place because that system uses 10 digits. So what do you think we're going to multiply by in the binary number system? 2. Perfect, because we have 2 digits. So we have the ones place. 1 times 2 gives us the twos place. 2 times 2 gives us the fours place. 4 times 2 gives us the eights place. And we could keep going if we wanted. We'll stop for now, though. It's important to remember that every time we add a bit, we're doubling the amount of values that we can represent. More on this in a little bit. So again, this means we have 1/8, we have 1/4, we don't have any 2s, and we have 1/1. We add those together and we get 13. So 1101 in binary represents the decimal value of 13. So the magic behind binary and converting decimal base 10 to a binary or base 2 number is figuring out which place values or powers of 2 you need to add up to get the number you want. So get out a piece of paper, and what I want you to do is copy this chart down, copy these place values you see here with the powers of 2 as well as the place values underneath. You can pause the video and then unpause when you've got this ready to go. Welcome back. So if we wanted to find the binary number for decimal number 41, we have to figure out which of these binary place values we need to add together to get 41. So we start with the left, and 128 and 64 are too big. So we are not going to use those two place values. So remember, binary uses 0 and a 1. A 0 is off and a 1 is on. So think of it like we're turning these two place values off. So we're going to put zeros right there. 32 is smaller than 41, so we can use that place value. And so we're going to use a 1 to represent the fact that we're going to use this place value or it's turned on. So now we have to figure out what's left over. So we just do a little math, 41 minus 32, and that gives us 9. So which place values do we need or can we use that's going to give us 9? Right, we're going to use 8 and 1. So that means we're going to turn those two place values on and give the place values we did not use, a 0. So 41 in binary ends up being 0, 0, 1, 0, 1, 0, 0, 1. Go the other way around and convert a binary number to a decimal number. We just see which place values are turned on with a 1 and we add them up. So go ahead and pause and see if you can figure out what this binary number is in decimal, and unpause when you think you've got it. Welcome back. So to convert this binary number, we're just going to add up the place values that have a 1 at them. So we're going to add up 64 plus 4 plus 2 plus 1, which is going to give us 71. So let's try another. Again, go ahead and pause. See if you can convert this binary number to its decimal equivalent. Unpause when you think you've got it. So let's check. So we are going to do a lot of math this time around, adding up 64, 32, 16, 8, 4, 2, and 1, which is going to give us 127. A little trick here though, if we are counting in binary, the more you work with binary and the more you count in binary, the more patterns you'll see. And one pattern that I'll point out to you right now is if the place values to the right of one of our powers of 2 is turned on, the value that that's going to add up to is going to be 1 less than our place value. So this, for example, was 127. Everything to the right of our 2 to the 7th place value, or 128, was turned on with a 1. So it's 1 less than 128. So let's try a practice question here. Go ahead and pause your video, read through this question, and see if you can figure it out, and then we'll go over the answer. Welcome back. Let's see how we did. So this says each student enrolls at a school, or that enrolls at a school is assigned a unique ID number, which is stored as a binary number. The ID numbers increase sequentially, so they're going to go up by 1, so you're counting, with each newly enrolled student. If the ID number assigned to the last student who enrolled was the binary number 10010011, what binary number will be assigned to the next student who enrolls? So there's a few ways you could have figured this out. The one way I will go through with you right now is just kind of doing what we've been doing. So you could have converted that binary number in the problem to a decimal number, right? Figured out which place values are turned on, add those together, and that's going to give you 147. So then what you could have done is gone through your choices, A, B, C, D, and figured out what the next sequential number is going to be. So looking for 148, converting those different binary numbers to see what you would get. And if you ended up selecting A for this answer, because that's 148, then you did awesome. Good job. So earlier I said that when we add a bit, we double the amount of numbers we can store. So let's see if that statement is actually true. If we have 3 bits and they're all turned on, so a bunch of zeros and then 111, this means that I can count up to 7, but I could actually store 8 numbers because 0000 is also a number. Now, if I add just 1 bit, making this 1111, now I can count up to 15, but I can store 16 numbers because don't forget about that 0, which is double what I could store with just 3 bits, which was 8. So here's a good formula to remember. N being the number of bits, so we would write our powers of 2, or the number of bits we have, like this, 2 to the n. So 3 bits would give us something like this, 2 to the 3rd, which equals 8, like we just saw, 8 different values that we can store with 3 bits. So 2 to the 3rd, again, tells us that 3 bits are turned on and we can represent 8 different numbers. Again, go ahead and pause your video, read through this question, figure out your answer, and then we'll talk about it. Welcome back. So this question is asking you, 1 byte or 8 bits is enough to represent 256 different values. How many total bits do you need to represent 512 different values or different numbers? If you said 9, because adding 1 bit gives us double the amount of numbers that we can store, then you are spot on. Excellent job. So what did we learn today? Well, we definitely learned and practiced a whole bunch of how to calculate binary to decimal and decimal to binary. So that's it for today. I'll see you soon. Bye-bye.